Welcome back to Physics 141 Online. I'd like to do an example problem involving the use of Newton's laws to solve a problem with circular motion. So here, read the problem. A wrecking ball with mass m is suspended from a cable of length L and is in circular motion, where the cable makes an angle theta from the vertical, and the sketch shows this pretty clearly. So first we want to find an expression for the tension in the cable in terms of the given quantities, and then if we know the cable's length and we know that the maximum strength of the cable, the maximum load it can support, is 5 times the weight of the wrecking ball, what's the maximum safe speed for the circular motion? And you might have seen something like this at a construction site before, where there's a crane and there's either a wrecking ball or there's some other large heavy object suspended from a cable, and as the crane moves around, sometimes this object gets to moving in circular motion, indicated here with the dotted horizontal line. So this mass, this wrecking ball M, is moving, and I'll just draw it here with a little arrow. It's moving in the circular path in some sense like that. And we will eventually have to solve for the maximum speed that it can travel. And I think it's pretty intuitive, if you just think about it, that the faster that object travels, the greater the tension will be in the cable. We'll be able to show, using Newton's laws, that that's actually true. And we'll be able to find the maximum safe speed. So this is clearly, if we go back to our problem-solving strategy, right? If we look at the identify, this is clearly a Newton's second law problem, Newton's laws in general. Then, in order to set up the problem, we always start Newton's law problems with free body diagrams. And so the setup involves a free body diagram, and this problem is a little simpler than some that we've done because there's only one object here. There's only one mass. And if we think clearly about it, there's only two forces. So there's the weight, the earth pulling down on the mass, and then there's the cable, which is oriented up like this. We'll label the force T, and we see that if we draw in a dotted vertical line here, then that angle theta, right, is that angle, but it's also, using a simple theorem from geometry, it's also the angle here. If we have two parallel lines, which are the dotted lines, and they're intersected by a line, then they create these two angles that are the same. And so the tension force makes an angle theta with the vertical. And now we choose a coordinate system so that we can write down Newton's second law. And here we have to be a little bit clever, because if we look at the circular motion, we know that there must be a net force, or at least a component of a force, acting towards the center of the circle. And clearly that's going to be supplied here by the tension. So the horizontal component of the tension is pointing to the left, which in my picture is toward the center of the circle. So when I choose my coordinate system for this problem, I'm going to choose the y direction, as you might expect, to be positive upward, but the x direction to be positive going to the left. And you'll see why that simplifies things in just a minute, because this tension force has a component going to the left. So we've got the free body diagram, we've chosen a coordinate system, now we apply Newton's laws, and we apply them along both directions. And so we have the sum of the forces in the x direction on this mass has to equal the mass times its acceleration in the x direction, and then we're going to do the same thing for the y direction. Sum of the forces in the y direction is m times the y component of acceleration. On the left-hand side, the only force we have is the component of the tension that's in the horizontal direction, and you can see that that would represent the side of the triangle that is opposite the angle theta. So the tension force has a vertical and a horizontal component. Here, according to my coordinate system, it would be T sine theta, and it's positive because the way I've chosen my coordinate system, it's pointing to the left. And then on the right hand side we have mass times acceleration. Well, if this is circular motion, then the acceleration that points toward the center for uniform circular motion always has to have the expression v squared over the radius. And that's also in the positive direction here because the acceleration points toward the center of the circle. If I had chosen my x-coordinate to the right to be positive, then both sides of this equation would have minus signs in front of it, because the force would be in the negative direction and the acceleration would be in the negative direction. So I'd get the same answer, but I would just have minus signs on both sides. So we'll call this equation 1. Now let's do equation 2. Let's do the vertical component. We see the only forces in the vertical direction are T cosine theta, which is the vertical component of the tension force in the cable, minus mg, which is the weight. And here, as this object travels in the horizontal circle, it doesn't rise or fall, and therefore doesn't have any acceleration in the vertical direction. So this is a part of the problem that we just have to be alert and realize that that's a simple expression that we can write down for the acceleration. So this is equation 2, and it looks like I might need to combine these two equations. But first, let's see what I can do with equation 2, just solving for the tension. Part A says find an expression for the tension in the cable in terms of the given quantities and g as needed. So from equation 2, if I add mg to both sides and then divide by cosine theta, I get T equals mg over cos theta. And if you just look at the way the problem is stated, you realize, hey, that is the answer to part A, because it gives me the tension in terms of the mass and the angle and of course the constant g, which is the Earth's gravitational acceleration. So I've got the answer to part A right here. So let's move on to part B. Part B says if the cable has a certain length and can support a maximum load of 5 times the weight of the wrecking ball, find the maximum safe speed for the motion. So what we're going to do now is solve for V. And then we'll figure out how we get the maximum V once we've solved for it. But we're going to combine equations 1 and 2 and solve for V. And the easy way to do this is just to sub equation 2, sub 2 into 1. Alright, so we'll rewrite equation 1, except in place of T, we'll write mg over cos theta. So what does that give us? We get mg over cos theta, that's our T, times sine theta equals m v squared. Whoops, let me fix that because I don't want to mix up my capital and small letters. So it's m v squared over r. And you'll realize that r is not given to us in the problem, but if we just draw in the radius and realize we've got a right triangle here, we can see that r is simply L times the sine of theta. So I'll write that up here, r equals L sine theta, and I'll make that substitution next, and then we're going to solve for v squared. So that means over here this becomes m v squared over L sine theta. Now look at this equation. I've got m on both sides, so if I divide both sides by m, it drops out. And then I can multiply both sides by sine, and then I can multiply both sides by L as well. So when I do that, I'm going to get Lg, and I'll have the sine theta twice, so it'll be sine squared theta over cos theta equals v squared. Alright, so let's take a breath here and see what we've got. Of course, I want to take the square root of both sides in just a minute, but what we have is an expression for v in terms of L and g and the angle. Now it doesn't seem to involve the tension, but actually we know that the velocity was related to the tension. We saw that in equation 1. So how do we find the maximum safe speed? Okay, we're told the cable can support a maximum load of 5 times the weight of the wrecking ball. What does that do? If we plug in the maximum value for t, then we can figure out the angle theta, or at least the cosine of the angle theta, which is all that we need. So for t max, we're told that that's 5 times the weight of the wrecking ball, so t would be 5 mg equals mg over cos theta. And look, the m's cancel out, The g's cancel out, and we solve for cos theta, and we get 1/5. And I don't even need to evaluate theta, because you'll see in just a minute how that expression is going to allow me to find the maximum value for v. So what do? Let me just, in order to get everything as simple as possible trigonometrically, v squared can be written as lg, and then remember sine squared theta is 1 minus cosine squared theta. That's one of our very fundamental trig identities. So now I've got an expression for v max, and the reason it's maximum is because where the tension is a maximum, that's where the cosine of theta is going to be a minimum. And since the cosine of theta is in the denominator, a minimum value for that is going to make a maximum value for the speed v. So let me now take the square root of this expression. We have lg 1 minus cos squared theta over cos theta, and I have all the numbers. So let me just go ahead and plug them in now. L is 20.0 meters. Always want to plug the units in. G is 9.8 meters per second squared. Okay. Now we know that cos theta is 1/5, so what I have here is 1 minus 1/5 quantity squared. And then the denominator is just cos theta, which is again 1/5. And that's all under the square root. Got to be careful about that. Everything in that fraction is under the square root. So first of all, we can check the units. We get meters squared over seconds squared, and when we take the square root, we'll get meters per second. That works. So I'll put the units out here, meters per second. That means we've done our algebra correctly. We haven't made any really silly mistakes. And numerically, when you crunch those numbers, you get a maximum speed of 30.7 meters per second. And it's hard to tell for sure whether that is reasonable or not, but it would translate to a speed in miles per hour of a little bit over 60 miles an hour. Seems kind of fast, but maybe because the cable length is so long, maybe swinging around in a circle like that, you could get to move in a pretty high speed. So at least it seems within the realm of possibility. So just to finish the problem, the units check out, and the value is at least somewhat reasonable. And so we finished. So let's just take a quick look again at what this problem involved. We drew a free body diagram for an object in circular motion. We wrote down Newton's second law for the two directions. One of those equations allowed us to solve for the tension all by itself, and then we combined the two equations like we almost always do in these Newton law problems, combining the equations for the Newton's second law in the two directions, and that allowed us to find an expression for the speed, and then we used the additional given information that told us the maximum tension in the cable, and that would translate into the maximum safe speed. So I hope this is helpful, and we will do more problems like this in class.